All right. Good morning, everyone, or good afternoon, wherever you're tuning in from. I think I'm going to get started here. Looks like we have some late arrivers, but I will get kicked off. Hello, my name's Troy Trushinsky. I manage the AIT group of Teradyne, and you're joining in today for what is intended to be the first part of a multi-part series um, of webinars covering data load protocols. So today's tutorial will cover basically these 4 points at kind of an overview level. So today isn't really about a lot of depth. It's about kind of setting context and providing, I guess, executive overview level. And then we will have follow-on webinars that delve deeper into several of the topics that we cover today. So please stay tuned. Thanks for joining today and stay tuned. Also, a little bit of housekeeping. So because it's a larger group, I have everybody muted, so it'll be kind of one-way communications, at least audio-wise. But there is a chat feature and a Q&A feature in here. Tim Fleischner, who is also on, if you can see the attendee list, is co-hosting with me. So Tim will attempt to monitor the chat and the questions while I'm presenting, so that he can get any answers to any questions back to everybody who's joining. And then also, please, even after the event, don't hesitate to send via the chat any questions or requests for follow-on, and we'll do our best to get back as soon as possible to everybody. So thanks again for joining. What we're going to cover today, again, is the ARINC 615A protocol. We'll cover the supported operations. So there's 4 main operations that the protocol supports. We'll also talk about the loadable software parts. So 615A is primarily used to load software onto an aircraft, and so those software parts that have to get loaded have to be packaged. So we'll talk at a high level about ARINC 615, which is the standard format for packaging those software parts. And then we'll kind of go under the hood a little bit and talk about specifically how the files are transferred in these load operations on the network. And then we'll also cover a little bit about the secure handling of software parts. Security in this arena has become kind of front and center in terms of focus, and there's a lot of change and new features and additional protocol specifications and handling specifications that are new and available now, and are also still some new ones in process that are coming. So we'll talk about that a little bit also. So again, this is a first part of a multi-part series. In the future ones, keep an eye out for those, for invites from us, and those are going to go into deeper detail of a lot of the items we're covering today. All right, so 615A protocol operations. Like I said previously, there's 4, I guess, main categories or main operations that the protocol provides support for. The first is a find. So the find operation is what the data loader uses to query, to dynamically determine information, the basic information that it needs to communicate with the target avionics systems on a network. So it's a kind of a dynamic data determination protocol. Then there's the information operation. This is an operation that 615A provides a spec for that gives a standard way for a data loader to query and then receive and display current configuration status information from an avionics system. So it's, in a nutshell, the way that the data loader asks the avionics system to provide its current software that's loaded, the rev levels of that software, and the part numbers of that software, so that it can be displayed to a user. Then there's probably the most used operation in 615A is the upload, and that's used to transfer loadable software from the data loader onto the aircraft system. And then downloads are a way to use a data loader to extract data files from an avionics system. So one of the most common use cases of a download is an engine controller. So most engine controllers keep diagnostic logs of data that can be used for predictive maintenance. And so the data load protocol download operation is used to extract or pull files down in a standardized way from an avionics system, such as an engine controller. might talk a little bit about the find information. So a find operation allows the data loader to obtain the Ethernet, so the MAC level address of the loadable avionics systems, the IP addresses of those systems, and to identify those targets and some specific information about those. It's a very, very simple protocol. If you're familiar at all with a ping on a normal LAN, where you're basically just saying, hey, to another IP host, tell me if you're there and tell me what your IP address is by responding. This is very analogous to that operation, but at the data load level. It's a ping of loadable avionics systems, or a ping of systems that speak the 615A protocol. So the first step is that the data loader will send out what's called an information request, or an IRQ. So that's sent from the data loader, and it can be multicast on a network to all the avionics systems. So I have a network diagram there that shows a network of MMRs, which is it's common on a lot of commercial aircraft that there's 3 MMRs, a left, center, and a right attached on a network together. So the information request packet goes out. I just took a snapshot of Wireshark here so you can see what that packet looks like and what this sequence looks like. It's very simple. It's a UDP packet. It's sent to port 1001, and it contains byte values of 0101 in the UDP payload. Then what you can see in packets number 80, 81, and 82 in that Wireshark capture is the avionics systems replying to that IRQ, or information request packet. So here, if we look at the IAN, that's the information request answer that comes back. In that packet, the avionics system gives the information shown in the table kind of center bottom of the slide here. So every avionics system that is data loadable has a target hardware ID. So that's a unique alphanumeric identifier of that type of target. So in this example, these MMRs would each, that's a specific type of hardware, would have a type designation. So in the case of the example in the table there, we're looking at a Honeywell flight management system and how it would report. So in the information answer packet, the avionics system provides back its target hardware identifier, again, a unique identifier of that. It tells you what type of system it is. So in the table there, it's a flight management system. It tells you the position. So most avionics systems are at least replicated. So they'll have like a right and a left position, or in the case of like these MMRs, there's a right, left, and a center. So every responder indicates its position. And then it gives its literal name. This is usually a well-known name, a name that if you display in the data loader, a mechanic knows what that means. For instance, FMS left. And then there's usually a manufacturer's code, which tells who the manufacturer is. That's a 3-letter designation that ARINC disseminates and assigns to avionics manufacturers. So this is how a find works. Pretty simple. It allows the data loader to find who's there on the network and information like shown in the table below about the avionics system. So if we take a step back to just be able to communicate on an Ethernet or an IP network, an Ethernet IP network, which is what data loads are done over, the data loader and the avionics systems have to have their IP addresses administered. They have to know what their IP addresses are. If we use the analogy or the example of kind of a normal LAN, say it's just an office network, a LAN where you connect PCs or laptops that communicate. In those situations, typically there is a server or some kind of function. Usually it's embedded in the LAN switch, like a Cisco switch would have a server in it that manages the dynamic host configuration protocol, or DHCP is what you commonly hear it as. And what this function does is it basically, when a new PC or a new device connects to the network, it's used for that DHCP server to assign an IP address to that device that's connected to the network. And this is required so because you have to manage the IP addresses. You can't have 2 devices on the network with the same address. So that's what this is used for. But avionics systems are handled quite different than this. It's very rare to see an avionics system. In fact, you don't want any kind of real dynamic configuration of an avionics system. It's not as reliable, right? A dynamic system isn't going to meet the reliability standards required of an avionics network. So what that means is in data load applications, there's almost never, in fact, I don't know of any case where DHCP is used. So without DHCP, at a minimum, the data loader has to know what its IP address should be, and it has to be statically configured. So a user or some configuration that lives in the data loader has to know what IP address that data loader should have when it connects to an avionics network. It can't just connect without knowing that, like a laptop on a LAN, and then use DHCP to resolve. So what that means is typically inside of a data loader, you have to select a configuration based on the aircraft or avionics network that you're connected to, so that data loader can be statically given or told what its IP address should be to get on that particular aircraft or subsystem network. The other kind of housekeeping of note to be able to connect to an Ethernet network used for data loads is, okay, we've been talking about at the IP level, the host address, but to communicate with a loadable system or an avionics system, the data loader has to be able to resolve the avionics system's IP address into a MAC or Ethernet layer address. And this is always done on Ethernet networks with what's called the ARP protocol, or address resolution protocol. So one of the primary things that goes on when a find is initiated by a data loader is that it triggers the protocol stack in the data loader to do an ARP cycle to basically ask on the network what the MAC addresses are for the IP address that the find is being sent to. So I have a couple Wireshark capture snapshots here that show how this works. So if you see in the figure on the left, an ARP request goes out. So that is basically the sender is saying who has this IP address. And then what happens is whoever has that IP address replies back with an ARP reply and says, hey, I'm, in this example, 192.168.5.10, and I'm at MAC address 210000. So that's address resolution protocol. That has to go on initially on an Ethernet network for a data loader to be able to communicate with the avionics systems. And it's typically triggered through the find operation, through the process of the find operation happening. Okay, when we talk about ARINC 615A and data loads, really what we're talking about here is we're talking about transferring files. So at a baseline level, you have to use some kind of a file transfer protocol. ARINC 615A selected or uses TFTP, which is Trivial File Transfer Protocol. It's quite a bit more simple than the more common file transfer protocols used, like FTP. And so just in about one slide, you can get a pretty good understanding of how this protocol works. So it's a simple data block and acknowledge protocol. So if we look first at a TFTP read or a get file, the way that it works is the client side, the initiator who wants to read a file would send a read request message to the server or the system that has the file that the client wants to read. And then the server would reply to that with the first block of data. And when that's received, the client acknowledges it and so on. ACK data, ACK data, ACK data until the whole file is transferred. There are retries. So for instance, if the TFTP client receives data block 1 and it says acknowledgement back to data block 1, and then within some timeout it does not receive data block 2, then the client will resend acknowledge block 1 to try to trigger the server to resend the data block because it was presumably lost on the network. So there are retries. TFTP write or put files. So with that, the client or the initiator says, hey, I want to do a write. So it sends a write request to the server, which it's going to write the file to. The server acknowledges that, and then you enter your data, ACK data, ACK data, ACK sequence again. At the TFTP protocol level, there's really three main configurable program parameters. So you typically can, in the data loader side and in the target side, configure the block size. So that's the size, the amount of data that you want to put in each block that's sent over the wire. The baseline or smallest size is 512 bytes, but most data load operations use something up in the range of 8K blocks. It just causes fewer data and acknowledge cycles because you're getting more data bytes per data ACK sequence, and so it causes the data loads to go much faster the larger the block size. But it also means that you have a lot more to redo if there's a dropped packet and you have to do a retry, which typically is very rare. Dropped packets or dropped frames on a avionics Ethernet network is extremely rare. You also can configure at the TFTP level the retry timeout. So that's how long, say, after a client sends an ACK before it waits for the next data. And if it doesn't receive it within that timeout, it sends the retry. And then also you can say a retry count. So if you send a data or an ACK and it goes unreplied to, you can specify how many times you want to retry that before you declare the file transfer failed. So these are all settings that you'll typically see in the data loader side and in the target side of the protocol stacks. Okay, moving towards upload operations here. So an upload operation, the first thing that we need to talk about with that is if you're going to upload a software part using a data loader, the software part that's going to be uploaded has to be packaged into a standard format so that the data loader knows how to handle it. And that standard formatting is an ARINC 615 loadable software part, or LSP. And LSP format is pretty simple. I have a snapshot there in the image under simple LSP contents. Really, at a minimum, to construct an LSP, what you need to have is at least one file that's the actual software that's going onto the avionics system, and then a header file or a file with an extension of .luh, which you see there. What that header file contains, and the format of that header file is specifically what ARINC 615 specifies. That header file contains the part number of the loadable software part. It also contains the list of the target IDs. So if you remember back to the find operation, when a data loader does a find, the target avionics systems reply with their target hardware IDs. Well, a loadable software part has to have embedded in it the target hardware ID of the avionics system or the targets that that part is supposed to be or is valid to load onto. So this allows the data loader to not let an operator or a user attempt to load a software part to a specific avionics system that software part was not constructed for. Then the header file also contains the list of actual software files. So this is the list that's avionics system specific of files, and then for each of those files, a part number. So what I've shown, the screenshot here of the LSP header file contents, is actually a screenshot from one of our tools that you can use to view and construct ARINC 615 software parts. So this is kind of a graphical view of what is inside one of these header files. Then finally, the header file for a software part contains multiple CRCs. It contains CRCs calculated over each of the individual load files, and then a CRC that's calculated over the whole software part, which means over the header itself and all of the individual load files. And it's used to ensure the integrity of the software part. So when a data loader is presented or given a software part, what it will do is it will crack open this header file, and then it will check all these CRCs or calculate them itself, and then it will check them against those CRCs that are embedded in the header file to ensure the integrity of the software part before commencing to load it to the avionics system. Okay, if we look at the actual mechanics or the protocol progression of an upload operation, so I have some flow charts here. On the left side is the data loader. On the right side is the target avionics system. So an upload operation is initiated by a data loader. So the data loader initiates this by issuing a TFTP GET or a TFTP read request to the target system. And specifically, that read request is for a file that is named accordingly. It has the target hardware ID of the target, which is reported in the find operation, then an underscore, and then the position, which was reported from that target in the response to the find operation, and then a .lui on the end. So that a read request for that specific file name indicates to the target that a data loader wants to start an upload operation. The target either accepts or denies that operation based on what it puts in the contents of that LUI file. So that LUI file, the format and the contents of that are specified very specifically in ARINC 615A, and it allows for the target and the data loader to communicate about if the target is accepting that operation. After the data loader receives an LUI file from the target indicating that it accepts the operation, then what happens is the target will confirm that it's ready to start the operation by sending a status file or a file with a .lus. So it'll do a put request to the data loader with that LUS file. That LUS file format is also specified specifically in ARINC 615A, and it has specific fields that the target system uses to indicate to the data loader that it's ready for the operation. After the data loader receives that ready, what it does is it sends an LUR file, which is another file whose format is specified in ARINC 615A. It does, and the data loader does a TFTP put or write of that file to the target. And what that LUR file contains is a list of the loadable software parts that the data loader wants to load. Specifically, it contains a list of one or more of the ARINC 665 LUH or header files for the loadable software parts that the data loader is attempting to load. Once the target receives that LUR file, it then will go through and read from the data loader. So it'll issue a read request to the data loader for the header files that are specified in that LUR file. The data loader will then send those header files over to the target. The target can open those header files then, which contain the list of all the files, the actual avionics system files that are part of that loadable software part. And the target then uses that file list in the header file to sequentially read each of those loadable software part files from the data loader. While the target is doing this, it's simultaneously and periodically sending status information to the data loader in the form of the LUS files. So what you think of is after, or a good way to think of it is after a data load operation is accepted and the target has received the list of software parts that the data loader is requesting to load, the target will effectively be operating in two simultaneous threads. One thread is spinning through the load files listed in the header file and reading them from the data loader. And then there's a simultaneous thread that is sending or putting status in the form of LUS files to the data loader to indicate to the data loader and the user of the data loader the status and the progress of the upload operation. And so it continues like this until all the files are transferred from the loader to the target. And once that is completed and the target accepts those files, the target will write a final LUS file to the data loader, and inside that LUS, it will indicate that the operation is complete. To kind of see it in terms of what happens on the network, I have a screenshot from a Wireshark, so a packet capture from a network when an upload operation was executed. This was a very simple, small load. This was actually a load of a flight management system OPC. So it was a configuration file for a flight management system, which is typically a one software file, loadable software part. So you can see in the first three packets there, that is the TFTP file transfer of the LUI. So that's the data loader requesting the target to read the LUI, and then with the data and the ACK there, that is the actual file being transferred. Then after that, we can see that the loadable target initiates the transfer of the LUS file, indicating that it's ready. After that LUS is transferred, you can see that the data loader initiates a put or a write of the LUR file to the target system. And then once that LUR file, which has the list of the software parts, is received, below that you can see the block of packets exchanged as the target writes status files and then simultaneously reads the LUH and the loadable software part file, the LUP there, about halfway down. So that's a very simple, compact, small upload sequence of the 615A protocol. So next I'm going to go into covering a little bit about the handling of software parts, and more specifically the secure handling of software parts, which is kind of a front and center topic in the world of data load right now. So first, just kind of setting the context here, showing the flow of software parts. So you can kind of think of it typically as aircraft manufacturers and manufacturer of avionics systems. They are responsible for constructing and packaging the software parts that ultimately have to get out to and updated on the aircraft by the airline or the operators of those aircraft. So typically you have the software part, which is constructed at the avionics or aircraft manufacturer. It's then provided to airline or the aircraft operator engineering teams, who then distribute those software parts out to data loaders and maintenance groups, and indicate specifically which aircraft and which systems those software parts have to get loaded to. Examples of software parts or types of software that is periodically, on weekly or monthly cycles, distributed from manufacturers through operations engineering teams out to aircraft are flight management system navigation databases. So FMS systems typically require that their nav databases are updated at least once a month. There's also ground prox warning systems on aircraft, and those have to have terrain databases that are updated, usually monthly also. And then cockpit display systems. So a lot of the newest display systems in the cockpits are, large screen format with a lot of functionality packed into a single screen. And so there is commonly updates to those to provide more information to the pilots and the operators of the aircraft. So these are kind of the typical types of software parts that you see going out to aircraft regularly and periodically. So we talked about that those parts have to be, in order to be used by a data loader, they have to be packaged into an ARINC 615 loadable software part. But also, you can optionally sign those software parts. So that means attaching a digital signature in a process similar to this. So the first thing would be at the software provider in step one. So this would be the aircraft manufacturer or the avionics system supplier. The software part would be digitally signed and put into a crate. A crate is a zip file that basically contains the software part, the ARINC 615 software part, and then an XML file which has a manifest of the software part or parts that are in that crate, and then also a digital signature for that crate. Then when that crate is received by the aircraft operator, the software part is extracted. So the operator would take the software part out of that crate and check the signature to ensure that that part came from the known supplier so that it's authentic, the part. Then the operator would re-sign that part, basically indicating that I accept this part and I am putting a signature on it to say that I am validating or authenticating this part to be distributed to a data loader and loaded onto an aircraft. And then at that data loader, the software part signature would be checked so that the data loader can ensure that that part is the actual original part that came from aircraft engineering. And because aircraft engineering checked the signature when it came from the software part supplier, you're ultimately verifying out at the PDL that that part has an authentic source, that it's the actual part that hasn't been corrupted since it came from the source. These digital signatures that are applied to the crates and the software parts use PKI methods. And the main thing here, again, is to ensure the authenticity of the software parts, that they're authentic and the original part that came from the original manufacturer of the avionics system in that part. So software parts use the PKI system or method. software part signing uses the PKI method. So they're signed using a public-private key pair. So the signer or the manufacturer of the software part has a private key signing certificate. So this is something that is kind of their keys or their unique identity. It's the public key signing certificate is usually held very securely in an encrypted format by the signer. And then all receivers of those signed software parts are given access to the public key part of the public-private key pair. That public key is used by the receivers to match up with the sender's private key to ensure that that part came from the sender who you think that it came from. This is a fairly complex topic. What's being provided here is obviously very topical level. This is specifically one of the areas that we will have one of the follow-on webinars to delve much deeper into. But kind of in a nutshell, or to summarize here, why use digitally signed software parts? Well, ARINC 615 and the packaging into software parts, as we described, uses CRCs, which can be used to ensure the integrity. So basically that can be used to ensure that that software part has not been corrupted since the last time it was packaged into a 665 part. But for example, if a bad actor intercepted a software part between the manufacturer and the operator, or the whoever's going to load that part could be corrupted or changed, and then it could be repackaged into a 665 part and then passed on. And the receiver of that part would have no systematic way of knowing that that part was changed en route, and it would still have integrity because the CRCs would be recalculated after it's changed. So what digitally signing a software part does is it allows the receiver of the part a method to verify the source of the part, to verify that that part was signed and packaged by a known entity, a verifiable known software supplier. So that's kind of covering the handling of software parts and the upload operations. Next, going to talk just a little bit about a couple of the other operations that are supported by 615A that we alluded to at the beginning. So the other, after uploads, the next most common operation that you'll see done with a data loader is an information operation. So like I mentioned previously, this is where the data loader uses a standard method to read from the target its current configuration status. So basically the target provides to the data loader the currently loaded software part numbers and versions, and also it can provide hardware part numbers and serial numbers to indicate the current hardware configuration status also. The data loader initiates an information operation by doing a read request of a .lci file. So the operation starts very similar to the way an upload starts. The target either accepts or denies that and indicates that in the contents of the LCI file that it provides to the data loader. If accepted, then what happens is that the target system will do a write or a put of its configuration information in the form of a .lcl file. And that's, again, a standard format specified in ARINC 615A. And just like the data load operation, while the target is basically collecting and constructing and sending that configuration information in the LCL file, it will have a simultaneous thread operating, which is providing periodic status updates to the data loader about the progress of that operation, and ultimately also indicates that the operation is completed. Similar to what we showed with the upload operation, you can see a sequence of packets for an information operation here. So you can see the first 3 packets there is the initiation with the LCI read request initiated by the data loader. Then the operation is accepted. The target writes the LCS file to the data loader to indicate that it's ready. And then it periodically keeps sending the status updates with the LCS. And in the middle there, it sends the actual configuration data in the .lcl file. And then at the very end, sends a final LCS indicating that the operation's done. I have a screen grab here of what that configuration data looks like when it's received in a data loader or a portable data loader application. And really, it's just a hierarchy of part numbers and amendment levels, and then designation or a kind of a user or manufacturer definable text field that can be used to tell more information about that part in its config level. ARINC 615A also provides support for downloading files, like we talked about at the beginning, for instance, downloading statistics and performance files from, say, an engine controller. There are two types of downloads that are supported by ARINC 615A. One is a media-defined download. With this type of download, what happens is the user and the data loader have to tell the avionics system specifically by name which files that they would like to download. That file name list can be stored in a standard file format, which has an extension of a .lnr. And then there's also the operator-defined. This is a more interactive download. With an operator-defined download, what happens is the data loader and the operator of the data loader will first query the avionics system and say, hey, avionics system, give me the list of files that you have that are downloadable. When that list of files is received at the data loader, then the operator or the user of the data loader can select which of those files they would like to download, and then they continue by then going, and the data loader does TFTP read requests to read those files from the avionics system. The operator-defined download is fairly more complex because you have a sequence of, basically query, get the results from the avionics system, then send back from that query which of the files in that list you would like to download, and then do the download. So it's a little bit more complex to implement on the target avionics system side. So I would say, in my experience, the media-defined download is more often what's implemented in real networks. That's what I have covering kind of the intro tutorial here. I've got a couple slides of promotional here. So at AIT, we provide a full suite of data loader and target side solutions. So if you have any questions about what we offer for portable data loaders, so data loaders used out at aircraft in operational settings, let us know. We also provide data loaders that can be used in the shop for loading avionics systems when they're off wing or when they've been pulled from the aircraft and they're in the shop. And then we also provide protocol stacks in terms of embedded software for both the data loader side and the target side, so that you can embed our data load functionality in maybe your own implementation of a data loader or on an avionics system. If you don't want to write the whole target side stack, we can also provide that as a software library that can be integrated on an onboard system. We also provide a full suite of software packaging, so tools to create ARINC 615 loadable software parts and package those into media sets, and then also tools to digitally sign those software parts. And then we additionally, in conjunction with that, provide systems for distributing that software and handling it. So enterprise applications to take the software parts and distribute them out to PDLs and different sites that could be located throughout the world. The summary here. So we talked about the 615A data load protocol today. It defines data loads over an Ethernet LAN network using IP and UDP. 615A supports uploading, so moving software from the data loader and updating it into the avionics system. Also supports downloading, so pulling the data from the avionics system down to the data loader. And then also an information operation where you can query the avionics system to extract and show to the operator of the data loader what the current configuration state is of the system. ARINC 615A uses a very simple file transfer protocol called TFTP to actually move the files. And the loadable software parts that are uploaded using 615A are packaged according to the ARINC 665 standard, which includes features to ensure the integrity of the software parts. Loadable software parts can also be optionally digitally signed, and ARINC 835 is the ARINC standard that defines the methods for digitally signing those parts. And digitally signed parts ensure the authenticity of the software part. It ensures that the software part really came from a trusted source. And then finally, I'll close with if you're interested, if this was helpful today, please be on the lookout for future, more in-depth webinars covering each of these topics, but in much more depth going forward. So thanks for joining today. I don't know if there were any questions asked in the chat.
We did have one question, Troy, that I thought
okay, good.
Answer aloud. So the question was, do you expect the Ethernet network to be able to transport jumbo frames in order to support the 8K data blocks?
No, our data load solutions don't. So if you have an 8K data block, we could support that operation over a network that had an MTU of as low as 64 bytes, because the IP layer that's used supports fragmentation and reassembly. So you can send large blocks of data, 8K blocks of data, and not be required to support jumbo frames at the MAC level, because IP provides the method to fragment and reassemble those large blocks.
That was the one question that was
Okay.
submitted. So I don't know if anybody else has any questions. They can type them in. We can be on the lookout and stay on for a couple minutes.
Okay. And I will also end with, I recorded this session, so there will be a recording available. I'll make sure and make that available to everybody who joined in, since I've got your contact information. And then, like I said, please look out if you're interested. We'll be doing more of this in the coming weeks, over the next several months here. And also, I'll mute and put on hold here, but I'll leave the meeting open in case you want to take a few moments and send in any chat or questions. We'll try to respond digitally for at least a few more minutes here. So thanks for joining today. Appreciate the interest and appreciate the attendance. Have a good day.